Hello, everyone, and today's lecture we're going to start talking about some of the more modern optimization algorithm using the basic framework of a gradient descent algorithm and their improvement. We'll talk about this in chapter 8 of our textbook lectures, but here we are going to give you some of the hands-on experience with the several algorithms we introduce. We have been introduced several enhancements to the gradient descent algorithm. The first one is momentum, and using the current improvement and the past improvement as a exponential function for how firm we are on the current direction. Second one, we did it with Nastrov momentum, is improvements of momentum algorithm. And the third one we're dealing with, we'll talk about is gradient, adaptive gradient algorithm. Then we trying to improve the adder gradient to using RMS probe. And this is using the root of mean square errors as one of our gradient corrections, actually, momentum and gradient correction. Then we're dealing with so-called added delta. Is another improvement of RMS probe. And then we talk about two other algorithms. One is the atom algorithm, and we mentioned that atom algorithm is currently all the researchers and practitioners recommend this atom algorithm, and that's why we start our lecture with this atom algorithm to begin with. And finally is the so-called hypergradient algorithm. We talk about several of those, but today we're going to start talking about atom algorithm to begin with. Okay, using some of the lecture notes from the other class, but here what we're trying to focus on is these atom algorithm. So here we talk about gradient descent algorithm before, and the mini batch gradient descent methods is also very efficient. Instead of doing the gradient for all the coordinates, they're using a smaller size of a coordinate as part of the gradient descent. And so this is so-called mini batch gradient descent method is we show some of the I have shown some of the so-called using for parallel machine or multiple graphic processing units. Then we talk about we will talk about momentums and adder grades and RMS probe. So these are the algorithms we're going to start talking about. Atom was proposed not long ago. It's 2014. It's about 8 years ago, and this algorithm was originally proposed for machine learning process, and it shows has most effective. And I want to demonstrate the effectiveness is not only for the so-called nice function. We have a so-called convex function. Atom algorithm is more for a global optimization. So he has a first order momentum and a second order momentum from the current gradient information, so that it can jump out of a so-called local minima and search for global minima if the case. However, the Adam algorithm actually has some issue we will discuss later. And also, in 2019, Adam algorithm can be shown to have a poor performance and variance control, and sometimes can be not converging at all. So let's go over the review the Adam algorithm from before we talked about, but one more time. And this algorithm is the key component we have for the Adams algorithm is the first order momentum V and the second order momentum S. And what is the the V is just the so-called exponential smoothing between the current momentum to a current momentum and the current gradient information using a weighted beta 1 and 1 minus beta 1. Also, the second order momentum is exponential smoothed, so-called beta 2 times the current squared of second momentum S plus 1 minus beta of the gradient squared. So it's just gradient squared momentum. And the first momentum gives you plus or minus information as well as this certain type of magnitude of the gradient. The second momentum only focuses on the magnitude of the gradient instead of the sign of the gradient. So here we have a 2 beta for the so-called exponential smoothing factor. Beta 1 and beta 2 are non-negative weighting parameters. Commonly, beta 1 using about 0.9, beta 2 is 0.999, almost 1. So we're trying to give the current momentum, second order momentum, the highest trust, and the current gradient square is very little impact. So, so we can actually calculate the G prime, the corrected first order and corrected second order, V hat and S hat, and divided by current momentum divided by 1 minus beta t. And the second order momentum is st divided by 1 minus beta 2t. Then we can use these V hat and S hat to calculate the G prime. And this is pretty much the so-called the equation RMS prop doing. And then we update our current solution, the new solution with xt equals to xt minus 1 minus the G prime. So it looks like the Adams algorithm is mimicking some of the parameter we use, some of the update equation we use for RMS prompt. However, they keep 2 different momentum, first order and second order. Okay, so we go into implementing the Adam algorithm. First, we're going to use the Rosenbrock function we used many times before our before this lecture. First is we want to calculate the objective of the Rosenbrock function and the first derivative of Rosenbrock function. Okay, then we perform a 3D plot of this surface plot for the Rosenbrock function, and this is the using matplotlib. Okay, and also we can do a so-called contour plot for the Rosenblock function. Actually, the minima is around here. So actually for this function, the minima is at 1, 1, 1, 1, 1, 1, and the objective function equals 0. So the red place is high, and the blue, dark blue is the lowest region. Okay, so we're going to define a function called Atom, and this function is gradient descent algorithm with the add and update. So several of our lecture we're talking about is using the same framework for this gradient descent. It's just the update of parameter and momentums and gradients a little bit different for each one of the algorithm right here. So let's go through this. And Atom algorithm, you need objective function, derivatives, bound, number of iteration, maximum iteration you want to perform, the alpha, beta 1, beta 2, and the convergence criteria, or a positive number, which is very small positive number. And alpha is the step size, beta 1 is the first momentum update smoothing factor, and beta 2 is the second momentum, which is a gradient square update function. All right. Then we have this initial solution. I'm randomly generated initial solution between the lower and upper bound. Okay. I show you later on how I define the lower and upper bound. Then we calculate first initially what is the initial solution's objective function. We call a score. And here we have I have two different so-called all score compared to the new score and minima score so far, and using as a indicator. And V to be initialized, okay, and set it all to 0. S is set it all to 0 as well, which is second order momentum, initialize the first and second order momentum. Then we're going to my main for loop and calculate the derivative, okay, for the momentum. And then we have an inner for loop and calculate, update the first order momentum, second order momentum based on the equation. Then we calculate corrected first order and corrected second order. So V hat and S hat are corrected, okay? And then we using our equation to update the from the current solution to the new solution, and we loop through that. After we update for this whole loop, and then we calculate the next iteration solution and update their objective function value, okay? And then we print out the so-called, what is the current solution? T is the time, okay? T is the time. T is current time, all right? For number of iteration, current iteration. X is the current solution, and score is the objective function. So if score is less than the minima score, then update the minima score and store the minima score solution. And also I test if we should stop the algorithm early. So O score minus the new score is less than 10 to minus 5. If that's satisfied, I'm saying convergence criterion satisfied, and then I print out the solution, okay, or return the solution. Otherwise, I'm storing the new score into the old score, and then we're looped from the next iteration. Okay? After all the maximum number of iteration exhausted, and then we print out what is the minimum score and solution, then we return xn score. So here you can actually return the so-called minimum score instead of score, return the minimum x instead of x. Okay? So it's up to you how you want to maintain this. Here is my main program to call this atom function. All right. The main program import the square root, array for NumPy, random function, and the C function. I want to use the C function so I can try my program using different parameter and just make sure every time I start with the same set of random number. So I'm using a C, and also I'm importing the so-called timeit library to calculate how much time, execution time, and what is the time elapsed? Well, actually, it's not execution time. It's the clock time, wall clock time for running this algorithm. Okay, and of course we set a firm fixed C101. So every time I rerun this program, it will start with exactly same sequence of random number. And I can actually using different random C to begin, and I can also test, with a different set of random number how my algorithm perform. But during the development, I'm using fixed C, and to make sure every iteration I come up with the same same sequence of a random number to see to isolate the difference in the result only because of the algorithm itself, is not because the random number I have. Okay, second is set up the bounds for my search optimization range. So X, as I set it with -1 to 3, and Y range is -1 to 2.5. It doesn't really matter. And this is the bound we use for generate randomized initial solution. Okay, and you can actually using a fixed initial solution right here like this. So all right. So I defined the maximum total iteration I want to try is 1,000 iteration maximum. And the step size is alpha equals to 0.8 for this example. And typically I start with trying step size with 1.0. This is 1 as a standard formulation. And the factors of first order momentum I'm using, and as suggested, we're using 0.9 as suggested. And factor for the second order momentum, I'm using 0.999 as suggested by the literature. And then I can run for the atom solution to tell me what is the best score and atom. All right. So what I need is a function to calculate the objective function value, to calculate the derivative value, and to give the initial bounds for the search uncertainty, maximum number of iteration. Alpha is the step size, okay, equals to 0.8 right now. Beta 1 equals to the smooth factors for for the first order momentum, and beta 2 equals the smooth factor for the second order momentum. Okay, and I'm using the starting time and ending time to calculate the time difference. Okay, here we have a time delta equals to second, and end time minus the starting time. So also I'm calculating the, I print out the final score I have. Final score is the final objective function. And this trial I'm running takes about couple hundred, oh, more than a couple hundred, I didn't realize. It takes about 500 some iteration, I think. Yeah, takes almost 600 iteration and to converge. So old score minus the new score, and the difference is absolute value is less than 10 to the minus 5. Okay, and then the optimal objective function and solution I have is 0.94, 0.97, and this is the objective function value, and it takes about 6.3 milliseconds to solve this problem. So even though we run about 600 iteration, however, the execution time is only 6 milliseconds, so it's not that significant. The algorithm itself is pretty straightforward, and as we stated in our lectures as well. So this is just a hands-on experience of how you put it all together. I want you to make sure you have a experience about this. Okay, and the next things we want to target is a nicer function. See if the atoms work, how well the atoms algorithm, gradient descent algorithm with the atom update works. So I changed it back to the objective function x squared plus y squared, and this is the first derivative 2x and 2y as a derivative. I'm using the same algorithm to solve it, okay, and using search range with a -1 to 1, and I only want to run 60 iteration, alpha equals to 0.02, and beta equals to 0.8, and actually we can use 0.9, for example, like this, and follow us what it have. So this function takes about, take all the 60 iteration, but you can see that converges quite nicely in this case. And also I plot the improvement of the trajectory for each one of a solution on this contour chart. So you can see how well the Adams algorithm work on the regular convex function instead of Rosenbrook function we have is we call a banana shape of a level set. It's a little bit easier problem, and you can see they converge quite nicely. And also I didn't put any of the convergence criteria to stop the algorithm because I want to see how well they the convergence trajectory. So using up all the 60 iteration in that sense. Okay, and the rest of the notebook I'm not going to go over is using a D2L is one of the newer machine learning suite and deep neural network training suite we're using for most currently proposed by a bunch of Amazon employee, and actually Amazon's behind this this project called D2L. Is using this D2L is very flexible, higher level neural network modeling language. I hope I have a time to explain this. They have actually a book talking about this, and This D2L can be using with the so-called PyTorch neural network framework proposed, supported by Facebook and their employee. And also we have the most famous TensorFlow. You can using D2L as well. TensorFlow is supported by Google. So D2L has a higher level neural network modeling language, and then which also can adopt into several different deep learning or neural network framework. And I believe also he can do the IMSE982. IMSE982 is open source Apache framework for neural network training. And I'm sorry we don't have time to introduce these deep neural network learning. I will have a separate class talking about these details. But however, this example just showing you we can using the Adam algorithm, the update is fairly easy, and we can also using that to do our minimization and neural network training. All right, so I'm just keep the code here in case you are interested. We can go over this in a separate class. The summer class is a little bit short. I don't have too much time to go over these topic. Is not belongs to the nonlinear programming domain. Okay, so hopefully this give you some interesting insight on the Adam algorithm, how well they perform. Next one, I'm going to start talking about RMS probe. RMS probe is an earlier version of the Adam, and actually Adams and Ada data is based on inspired by this IMS probe. IMS probe is still a very efficient algorithm. Is the default algorithm for PyTorch, which is a Facebook version of deep neural network training, and it's still being proven is fairly efficient in that sense. I would like to introduce that in the next lecture video, so show you how efficient and why is PyTorch is still using the RMS probe. And I think the TensorFlow neural network framework, the optimizer by default is using Adam. So different framework using a different flavor of optimizer, but you now know the inside or what is under the hood for optimizing a neural network during the training phase. All right, so I'm going to conclude this set of a video. We see you in talking about RMS probe in the next lecture video. Bye-bye.